Uh, welcome to the doctor's talk, impact on noisy data and support vector machine and deep learning algorithms on edge computing device. I'm sorry if I mispronounced anything. Dr. Shrirang Ambaji Kulkarni is currently working as a postdoctoral fellow with the School of Global Health Management and Informatics, University of Central Florida. Before joining UCF, he has worked as an associate professor with the Department of Computer Science and Engineering at the National Institute of Engineering, Mysore, India. He earned his PhD in Computer and Information Science from Visvesvaraya Technical University in 2012. His current research work includes developing new algorithms for analysis of healthcare data using machine learning. And I'll go ahead and hand it off to you, Doc. You go ahead and take over.
Yeah. Thank you, Stephen, for the wonderful introduction. Right. And so the today's topic here is like impact of noisy data on support vector machine and deep learning algorithms on edge computing device. The most critical term over here is the edge computing device. So we need to focus this topic in the background of this particular platform that we call it as edge computing device. So to begin with my talk, I will focus initially on this particular platform, which we call it as the edge computing device. We all know that the introduction of Raspberry Pi has revolutionized the domain of Internet of, like we all knew that with Internet and through the access of websites and web pages and other platforms like email and chatting, people across the world could interact with each other. It just revolutionized the way people could communicate with each other. But the next thing that's happening in the internet is that even objects can talk to each other. Objects can control each other. And this is which we call it as the Internet of Things. Now, these wonderful sensors, when they are sensing the objects or sensing the environment, they produce a huge amount of data. And this huge amount of data is transferred to the cloud, where there are certain analytics that happen in the background and some intelligent information is produced. Now, this intelligent information is again sent back to the user based upon which he can take some actions, right? So this is how the typical infrastructure started developing with Internet of Things. But we in this particular topic, we are speaking of a platform called as edge computing, which in a way is trying to augment the capabilities of cloud computing by reducing the amount of traffic that flows on the network. So here we consider things like we consider Raspberry Pi, and we are focused on the Raspberry Pi 4. So here I have given a small depiction of how a Raspberry Pi 4 can be built into a cluster. Why we build into a cluster, we'll take up further. So here we have shown in the diagram that there is an 8-port hub, there is a master node, and there are slave nodes. All these nodes have similar capabilities. Of course, if we say a master node, it is but natural that if it has to collaborate with all these slaves, then certain higher capabilities it can have. We can think it in terms of memory and other capabilities. Since this is a small kind of setup, I've indicated the interconnecting device as a 8-port hub. If you have something greater requirements, like if you would like to build a cluster with more number of nodes, let us say something like 24 or 48, then you can go for a switch, and you can go for stacking of switch, and you can build a huge cluster. So in the background of edge computing device, we are discussing what is meant by a Raspberry Pi cluster. So if someone would like to ask, like, what is a cluster? A cluster is a set of connected computer nodes that work together as if they are a single more powerful machine. Here, there are different single nodes which are connected to each other, and they are behaving like a single powerful machine. So what are the questions that naturally arise? Do they have their own operating system, each of these nodes? The answer is yes. Do they perform independent tasks or do they perform the same task? The answer is they perform the same task. Yes. Are they usually connected by some networking infrastructure? Yes, by some high-speed local area network. So what are the applications of this cluster computing? The applications are like high performance computing to deliver more performance than a typical computer can provide. So these high performance computing paradigm was usually used to solve complex scientific and engineering problems. Like, to give a simple example, let us assume that we are given a set of numbers in an array, huge set like 1 million, and we have to compute all the prime numbers. So we divide that huge array into small arrays and give it to each of the node so that it computes the prime numbers within it, and all of that are aggregated by the master node and presented to the user. A common cluster size in many businesses is between 60 and 64 nodes, and it may range from 64 to 256 cores. So Linux is the dominant operating system for high performance installation. So which are the famous Linux operating systems for HPC? We have SUSE Linux Enterprise, and then we have the Red Hat Enterprise Linux 8. These are some of the operating systems to note. Now, can a Raspberry Pi cluster become an edge device? Recently, Kubernetes was developed to manage clusters, and it was built using Raspberry Pi 4 nodes. And it was using open source technologies like Python and Microsoft technologies like C# and Azure machine learning models. So there have been instances where people are building powerful edge devices with Raspberry Pis in a cluster mode. Now, this is one of the way of looking at things. The other way is if you want to exploit all these nodes in a parallel mode, many new libraries are coming up in the world of machine learning and deep learning. Eliphaz is one of the examples, which is an extension of Keras library. So at the end of the day, if this is the platform which we are visualizing for augmenting the cloud computing capabilities by reducing the load on the cloud computing and moving some of the intelligent decisions to be made on site through an edge device, then naturally it leads to the question like, what are the advantages of edge computing? Like I mentioned earlier, it reduces the data on the network. So the bandwidth is conserved and we don't have a lot of traffic moving on the network. It reduces the latency. Instead of the data flowing from n nodes to the cloud and decision being taken and returning back, the decision is being taken locally. And the data is visualized to be as more secure because now it is at the premises of the customer rather than on some remote server on a cloud stored in some other location. So these are naturally the advantages of having an edge computing platform. So keeping this in mind, so our work started focusing on Raspberry Pi 4. Raspberry Pi 4 was relatively recently launched somewhere in 2019, and it is the state of art of these Raspberry Pi family of machines. So what is a Raspberry Pi? You can treat it as a single board computer, right? So it's having a very great powerful processor. So when you look at a computer, what are the things that you focus on? You first look at its processor, its capabilities, how much amount of RAM it supports, what type of Ethernet connectivity it has so it can connect to the LAN and then to the global internet. What are the type of power supply it needs, how much amount of display it supports. Can we have two parallel monitors connected to the same machine? All these facilities, we start looking at it because it's a single onboard computer. So the processor that Raspberry Pi provides is the Cortex A72 architecture. It is a quad-core 64-bit ARM v8 processor and it works at 1.5 gigahertz. This is the latest processor that sits on the Raspberry Pi 4. What is the RAM? So the RAM, it provides, Raspberry Pi 4 provides the tiny computer in different modes, like it supports 2 GB RAM, 4 GB RAM, and 8 GB RAM. And it is based on the DDR4 concept. So the transfer speeds are drastically high. With the newest, it provides the support for the new USB 3.0 ports and also the USB 2.0 ports. So there are 4 ports, 2 USB 3.0 and 2 USB 2.0. Then it uses USB-C port for the power connection. And it has graduated from Bluetooth 4.2 to Bluetooth 5.0. It supports 2 micro HDMI cards for 2 4K displays at 60 frames per second using one Raspberry Pi. And finally, there is the way with the capacity of LAN increases. And now we are speaking of gigabit Ethernet. So the gigabit Ethernet connectivity is provided by Raspberry Pi 4. So this is our basic platform on which our experiments are going to proceed. Now, when we think of a platform, it's always good that we make certain study before we either purchase it, configure it, or install it. So I'm trying to utilize this platform, which PyData 2021 Global Conference and NumFocus have provided, to see that the participants learn what are the components that they need to buy if they have to assemble their own Raspberry Pi machine. So this was my official list. So it's better to always go to a official Raspberry Pi kits, because it's always safe, like they meet the requirements of that Raspberry Pi 4 computer. So it's always better to have an official keyboard. It's all comes to the memory card, or we call it as the SD card. We need to follow certain norms because there are certain compatibility issues. I went for Samsung Evo and I have gone to 64 GB. It is usually preferred to have a memory card up to 32 GB. Greater than that, there have been some issues, but I have taken the risk and I've gone for 64 GB. And I've gone, and this Samsung Evo provides the speed with class 10 and U1 compatibility. What is this class 10 and U1 compatibility? I'll tell you in the later slides. Basically, it is supporting very high speed transfer of data. Then coming to the screen, it's always prudent that we have a screen which is of small size, because then we can carry this tiny device along with the monitor with us, right? So I've gone for the Raspberry Pi 4 screen of 10.1 inches. I've not gone for the touch screen. It will be just a display device. Now the greatest thing that we need to keep in mind is the USB power supply. So I have gone for the official Raspberry Pi power supply because it gives the desired power to all the components and the components can work smoothly. So the model that I have purchased is Raspberry Pi 4 model B 2019. It supports quad-core 64-bit along with Wi-Fi, Bluetooth, and the main memory is of 4 GB. Now this entire thing was supported by a generous stipend from NumFocus that allowed me to purchase all these components. Now, when we think about the processor, Raspberry Pi stands for something called as ARM. So what is this ARM? It stands for Advanced RISC Machines. Most of us are used to processors which are manufactured by Intel and all. They follow the CISC architecture, that is complex instruction set computers. RISC stands for reduced instruction set. Now, these RISC machines emphasize on registers, the smaller and so naturally smaller instructions, and thus can achieve very high speed of executing. You should all know that registers are more closer to the computers than the main memory, right? So this RISC emphasizes the use of more registers with the processor. Also, the smaller size of ARM processors and low power consumptions make them the most suitable for miniaturized devices like Raspberry Pi. Now, we all know that we need to have an operating system that suits the Raspberry Pi. The famous operating system is the Raspbian. So again, Raspbian is based on Debian, which is a Linux-based operating system, but as highly customized for Raspberry Pi. So when Linux evolved, there were various versions, what you can say, brands of Linux. We had Debian, SUSE, Mandrix, Red Hat. So Red Hat and Fedora have gone more to the desktop and other high-end performing cluster computers. We saw the example of SUSE. Debian has been customized to Raspbian and it is working very fine with Raspberry Pi. So the popular versions of Raspberry Pi are VZ, which is based on Debian 7, Jessie, which is based on Debian 8, and Stretch, which is based on Debian 9. So even though Raspberry Pi can work only with Buster flavor of Raspbian, which was launched on 2019, the OS is still backward compatible with other old Raspberry Pi models. So far I've given you the background of what components to purchase for Raspberry Pi, which is a kind of recommended operating system for Raspberry Pi. Now we'll see how we can connect a Raspberry Pi to a monitor. So we connect it via our micro HDMI cable, and we need to connect a mouse and a keyboard via the USB. We need to install the operating system. So there is something called as there is a manager for installing the operating system, and that's called as noobs. It stands for new out-of-box software that makes our life easier to install the operating system. We need to extract the noobs downloaded, and then this operating system has to be written into our SD card, or preferably a micro SD card, like I was mentioning in my previous slide. So it is based on a class which ranges from 2 to 10, 2 being the slowest and 10 being the highest. Plus the ultra high speed class 1 makes the data transfer very high. As soon as we log in, we need to type sudo raspberry pi raspi config, and it allows us to have a screen like this, right? And in this screen, we need to choose the interfacing options, and we need to change the password. You should know that the default login is Pi and the password is Raspberry Pi. It is recommended to change your password. We need to enable the boot to desktop, and we need to select certain international options like language, time zone, and the keyboard layout. With keyboard, there is something interesting thing that most of these keyboards are configured to UK English, and most of the keyboards that we use are based on US English. So if you have not configured the keyboard, then some of your keys may behave in a very funny manner. So post successful Raspberry Pi, we can have a wonderful environment. So now we have a Raspberry Pi, we have installed all these things. Now we need to install the machine learning and deep learning libraries. Python is naturally supported by Raspberry Pi. During installation, make it a point that you upgrade all the installation packages. So all your network interface, your Wi-Fi interface, and your Python 3.0 is ready to support all your machine learning and deep learning packages. So I'll not be discussing over here how to install all the machine learning and deep learning packages, because that's a separate session in itself. We'll directly go to the topic of our paper, that how SVM reacts to noisy data and what are the issues, computational time issues with its training data. So we'll be discussing that. Why we are taken SVM as one of the topics over here is, till the advent of these deep learning algorithms and the more popular ensemble methods like deep learning, XGBoost, and LightGBM, SVM was the power performer in machine learning algorithms. It gave very high accurate data in terms of classification and regression, and it was like a kind of the preferred one, right? But with the advent of deep learning, support vector machines have become more legacy systems, and they have certain issues. What are those issues? We'll be discussing through our talk over here. SVM basically works in a hyperplane mode. It tries to find a plane that supports the maximum distance between the data points of classes. So here we are visualizing a binary class. It basically tries to define a margin that provides the maximum distance between the data points of given classes. So here, if you observe at the figure, we see that there is a large margin, which is the thing that is needed. Plus, we have data points which are very close to the margin, which we call them as support vectors, and these influence the orientation of the hyperplane. So if we have two features, we think of a straight line. If we have three features, we think of a hyperplane. Visualizing more than three features is difficult in terms of hyperplanes. So what are the advantages of SVM? SVM has generally been proficient, like I mentioned, to deliver maximum performance in classification accuracy. SVM is consistently found to be superior to other supervised learning methods. So SVM comes under category of supervised learning. What are the disadvantages? It takes more time for training, and it does not perform well when the data has more noise. We have taken deep learning multi-layer perceptron as our benchmark to analyze the performance of SVM. As you know, the deep learning algorithms have been performing extremely well in terms of performance issues. So what is a multi-layer perceptron? It has an input layer, a hidden layer, and a output layer. We call it as a feed forward network, and the learning happens through the backpropagation strategies. So this is how you build a deep learning algorithm in Keras. We initialize with a constructor called as sequential, because we want to stack layers on one top of the other. We add a hidden layer along with the input. We add another hidden layer. Dense is used for building the layers, and the output layer has just one neuron. We try to compile it with optimizer that is called as Adam, and the loss and the metric for error is mean squared error. Adam is preferred because it's the highly efficient optimizer. And then we train using the predictors, that is the independent variables and the dependent variable. And finally, the result will tell us we are ready to test it for our test data. So we have another benchmarking algorithm, that is logistic regression, and it is used as most of the times as a binary classifier to classify discrete classes, like whether a person is male, female, cat, dog, pass, fail. What we call it as the nonlinearity is provided by the sigmoid function available with the logistic regression. Why we have used it as a benchmark is because it is very efficient to train. Okay. So this was our first experimental scenario. We used Raspberry Pi B, and we saw that logistic regression was the fastest, and it gave us a computational time of 37.81 seconds. SVM was the worst. It took 3,949 seconds. You can imagine SVM running on deep learning. It takes a lot of time. So what we did here is we thought of using the built-in scikit-learn pipelining concept. Here we use a standard scalar function. So fit and transform the training data set and just transform the test data set. So applying that, we built a pipeline, and we used a linear SVC because it is known to be one of the fastest variant of support vector machine. To this, our data, we added a Gaussian noise. Why we added a Gaussian noise? Because we wanted to test the robustness of SVM when noise is done. And we saw that when we saw in terms of computational speed, the speed of SVM increased drastically as compared to the others, and it became highly competitive to deep learning, but still it was inefficient as compared to logistic regression. Okay, so then why do we take logistic regression? Before applying SVM, it is always a thumb rule that you apply logistic regression and see the performance. If not, go for SVM. SVM gives more better results, but the downside is the computational time involved. So we used area under curve to see how our algorithms perform. SVM with noise, we saw the area under curve. If it is 1, it is better. That means it is able to classify the discrete classes properly. If not, it is a bit hazy. So we saw that with noise, the SVM's AUC dropped from somewhere near to 0.83. Also, the accuracy dropped to 78.58% from 99.9%. So what is the conclusion? The conclusion is pipelining architectures and automating machine learning models has a good impact on constrained environments like Raspberry Pi. And SVM model outscored DLAN by 79.94% with Gaussian noise in terms of computational time. But the bottom line is SVM is sensitive to noise. We cannot run away from it. If the data is noisy, then we have to develop strategies by which noise is eliminated from the data set. so that SVM is better able to handle it. This is a thumb rule for all the legacy systems which are still using noisy data. So I just ran my presentation a little faster so that I may have some time to take questions. I take this opportunity to thank PyData Global 2021 organizer, NumFocus, and all the attendees who have provided me an opportunity to present my work in front of you. Thank you.
Oh, thank you too, Doctor. I'll give everyone a few moments to type up and whatnot.
Okay.
Yeah, I've certainly not, like, I've of course got a Raspberry Pi myself. I've never done anything quite that advanced. I just have it hooked up to a 3D printer to run it.
Okay, great, great.
But it has, oh, we've got one in here. Thanks. Have you considered using a Jetson Nano with GPU on board?
Yeah, that's a really great question. Like a GPU is meant for deep learning and is meant for more powerful machine learning. And Jetson Nano has provided a device similar to Raspberry Pi. But as I mentioned in my earlier slides, to begin with, I would like to build a cluster with Raspberry Pi because I have more control over it. But in future, definitely, I would like to migrate to Jetson Nano. Some of the things with Jetson Nano was, to begin with, it was relatively little costlier for me. But in future, definitely, I would like to build a cluster with Jetson Nano. And Jetson Nano is the way to go. But the only thing here is, I personally believe that Raspberry Pi has a more dominant community. Let us hope in the meantime that Jetson also comes up with a more vibrant community and reduces our learning curve of installing all these deep learning and machine learning packages, and is more receptible platform.
All right, that looks like the last one. I'd like to thank you again, and I'm glad to be your host. And you enjoy the rest of the conference and the rest of the weekend.
Yeah.
You have a wonderful day, Doctor.
Yeah. Thank you, Steven.